Hi there, class. I hope all is well with you and your family. So, today we're going to be continuing our work on gases and the atmosphere. Today we're going to be looking at the combined gas law. This is on page 41 to 43 of your gases and the atmosphere booklet. So, pretty much what the combined gas law does is allow us to combine Charles' law, Boyle's law, and the Gay-Lussac law. So in other words, we're taking those three equations and combining them so that we can start to work on problems that have three variables, so pressure, temperature, and volume, instead of only two variables. Okay. So the equation there is in the box. So it's P1 times V1 divided by T1 equals P2 times V2 divided by T2. So an easy way to remember it is to think about it being as Boyle's law, which is P1 V1 equals P2 V2, but with the temperature term in the denominator on both sides. So it's pretty much Boyle's law divided by temperature on both sides. Okay, so let's look at a problem where we can use this equation. So if we look at the sample problem, it says a gas at 100.0 kilopascals and 30 degrees Celsius has an initial volume of 1.00 liters. Determine the temperature that could support the gas at 200.0 kilopascals and a volume of 0.500 liters. So just like with the other equations we were looking at, the first thing you need to do is write a list of all of the variables so you know what they are. So from the question we know that P1 is 100 kilopascals, P2 is 200 kilopascals, T1 is 30 degrees Celsius, V1 is 1.00 liters, V2 is 0.5 liters, and T2 is what we're trying to find, so we put a question mark there. Okay, so just like for Charles' law questions, whenever we have temperature, it absolutely must be in Kelvin. So T must be in Kelvin. So we need to convert the temperature of 30 degrees into Kelvin. So to do that, remember to go from degrees Celsius to Kelvin, we add 273. So 30 degrees plus 273 gives us 303 Kelvin. Okay. So again, you have to always have Kelvin. So now that we have the variables straight, we can write the formula down so we remember what it is. So it's P1 V1 divided by T1 equals P2 V2 divided by T2. Okay, and then we just fill in the variables. So that would be 100 kilopascals multiplied by 1.00 liters divided by 303 Kelvin equals 200 kilopascals multiplied by 0.5 liters divided by T2. Okay. So again, we also need to make sure that all of the units correlate. So both of our pressures were given in kilopascals and both of our volumes were given in liters. All of the values always have to have the same units. So we don't have to do any conversions in this case because they all match. Okay, so we need to get T2 by itself. So hopefully you remember from some of our other videos, we can do a math trick where we just switch T2 and this entire thing on the left hand side around. So this can become T2 equals 200 kilopascals multiplied by 0.5 liters divided by 100 kilopascals times 1.00 liters divided by 303 Kelvin. Okay, and the kilopascals here cancels with those, the liters cancels with that. And since this Kelvin is in the denominator of another fraction, the Kelvin is going to pretty much flip up to the top. So we would enter that in our calculator as 200 multiplied by 0.5. Okay, and then we would say divided by open brackets. Then we have to open another bracket. So it would be 100 multiplied by 1 divided by 303, close bracket. Okay, and then we get T2 equals 303 Kelvin. Okay, so that's the answer. So we can see in looking at this question that the temperature didn't change. So T2 actually equals T1. And that's because if you look at the terms here, 200 times 0.5 is 100. So this term here is 100, and 100 times 1 is 100 as well. So this entire denominator here cancels with this numerator, leaving only 303 Kelvin on the top. Okay, so let's look at another example. So example number 1 says if I initially have a gas at a pressure of 12.0 atmospheres, a volume of 23.0 liters, and a temperature of 200 Kelvin, and then I raise the pressure to 14 atmospheres and increase the temperature to 300 Kelvin, what is the new volume of the gas? So in this one, again, we just have to identify all of the variables. Okay, so let's do that really quick. So P1 is going to be, let's write P1, V1, T1, P2, V2, T2. Okay, I initially have the gas at a pressure of 12 atmospheres, so that's the P1. Volume is 23.0 liters. Temperature is 200 Kelvin. Okay, raise the pressure to 14 atmospheres, so that would be P2. Okay, I'm told that the new volume is what we're trying to find, so I'll put a question mark, and the new temperature is 300 K. Okay, so now that we have that there, we can go ahead and start using our formula. So also note that our temperature is already in Kelvin, so we don't need to convert them, and the pressure units match and the volume units match. So let's do that. P1 V1 divided by T1 equals P2 V2 divided by T2. Okay, so that would become, that would be 12 atmospheres multiplied by 23 liters divided by 200 Kelvin equals 14 atmospheres multiplied by V2 divided by 300 Kelvin. Okay, so we want to get V2 by itself. So what we can do actually is, since we want to get V2 by itself, we can divide both sides by 14 atmospheres divided by 300 Kelvin. So pretty much what we can do with the algebra is say that, so we would pretty much bring the 300 Kelvin on top here. So it would be 300 Kelvin times 12 atmospheres times 23 liters. And then we bring the 14 atmospheres down. That would be 200 Kelvin times 14 atmospheres equals V2. Okay, so let's just go over that again. So to get V2 by itself, we want to divide both sides of the equation by 14 over 300. So dividing this side of the equation by 14 over 300 would mean that we're pretty much going to multiply this side by 300 over 14. So that's why the 300 goes here and the 14 goes there. So our Kelvin units cancel and our atmosphere units cancel, leaving only liters. So V2 would therefore be 300 multiplied by 12 multiplied by 23, all divided by 200 times 14. Okay, so that would mean V2 equals 29.57 liters. Okay, so I know that might have been a little bit difficult there doing the math in one step. If you wanted to, what you could have first done is multiplied both sides by 300 Kelvin. So that would have been 300 Kelvin multiplied by 12 atmospheres multiplied by 23 liters, all divided by 200 K. And then once you got that number, you could then divide by 14 atmospheres. It's just sometimes faster to do it all in one step. Okay, let's look at question number 2. So let's identify all of our variables. So it says the gas takes up a volume of 17 liters, has a pressure of 2.3 atmospheres, and a temperature of 299 Kelvin. If I raise the temperature to 350 Kelvin and lower the pressure to 1.5 atmospheres, what is the new volume of the gas? So again, let's write all our variables. P1, V1, T1, P2, T2, V2. So our P1 is 2.3 atmospheres, our V1 is 17 liters, T1 is 299 Kelvin, P2 is 1.5 atmospheres, V2 is what we're trying to find, and T2 is 350 Kelvin. So our temperature is already in Kelvin, so that's straight, and all of the pressure units agree, so we're straight there. So that's just P1 V1 over T1 is P2 V2 over T2. That would be 2.3 atmospheres multiplied by 17 liters divided by 299 Kelvin equals 1.5 atmospheres multiplied by V2 divided by our T2, which is 350 Kelvin. Okay, so again, if you want to do the math all in one step, you can, but I'm just going to show it step by step this time. So you're going to get V2 by itself. So we're first going to multiply both sides by 350 Kelvin. 350 Kelvin. So 350 Kelvin cancels with that. Okay. And then we're going to divide each side by 1.5 atmospheres as well. But we'll show that in the second step. So let's clean this up a little bit. So 350 Kelvin multiplied by 2.3 multiplied by 17. Okay, then we divide that number by 299. So that gives us 45.77. Here, and remember the Kelvin units cancel, so we have atmospheres times liters equals 1.5 atmospheres times V2. So now to get V2 by itself, we just divide both sides by 1.5 atmospheres. And then that whole term cancels. And the units of atmosphere cancel. So V2 is pretty much going to equal 45.77 divided by 1.5, and that's going to give us a final answer of 30.51 liters. Okay. So if we just look at this part here, if you wanted to do everything in one step to get V2 by itself, you would just take this term over here, the 2.5 atmospheres times 17 liters divided by 299 Kelvin. What you would do is bring the 1.5 atmospheres down and bring the 350 Kelvin up. Because again, you can do all of that math in one step. So for all of these questions, that's pretty much what you're doing. So I'm going to quickly do example number 3. But instead of talking you through it, I'm just going to write the solution down. I suggest watching it in half speed, just to make it a little bit faster for yourself. Okay, so that's pretty much it for this video. Again, just watch that last bit at around 0.5 speed. And if you have any questions, just let me and Mr. C know. Hope you have a good one.